Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Vorhies, your host. I'm the Editorial Director with Data Science Central and also the Chief Data Scientist for Data Magnum. I'd like to start off our event today by thanking Dell Statistica for sponsoring today's event. Dell Statistica is an integral supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. I'd also like to take this opportunity to mention and show our appreciation for some of our other recent sponsors, including Alteryx, Tableau, Microsoft, Exaptive, Pivotal, and IBM, to name just a few. Now, past webinars are available on demand at datasciencecentral.com, and if you haven't had an opportunity to view them, I encourage you to take a look. They provide very useful insight into a wide variety of topics of interest to our data science community. Today's webinar is entitled 5 Technical Tricks to Try When You're Trapped. And before we begin, I'd like to briefly review the format of today's webinar. Today's event will be 1 hour long. We'll have 2 presenters that I'll introduce in just a minute. There'll be 10 to 15 minutes of questions and answering following the presentation. And this event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. I'd also like to encourage our attendees to provide questions throughout the presentation. We'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. So I'm very pleased to introduce today's speakers, Dr. John Elder of Elder Research and Nuno Antonio of Dell Statistica, EMEA. Dr. Elder is the founder and CEO of Elder Research, leads the largest and most experienced data science consulting firm in the U.S., and for 20 years the team has applied advanced analytics to achieve high return on investment for commercial, security, and investment clients in fields from text mining and stock selection to credit scoring and fraud detection. Now, John has engineering degrees from Rice University and the University of Virginia, where he's also an adjunct professor. He's authored innovative tools, is a popular keynote speaker, and has chaired several international analytic conferences. John served 5 years on a panel appointed by President Bush to guide technology for national security. He's co-authored 3 books on data mining, ensemble modeling, and text mining, 2 of which won Prose Book of the Year awards. Now, Nuno Antonio comes from a data science background and started his career as a researcher in modeling carbon retention in the paper and pulp industry. He later became a data and text mining consultant in areas such as manufacturing, security, marketing, and healthcare. He spent 10 years at StatSoft before Dell's acquisition, where he was regional manager for Spain and Portugal, and later in South America. Nuno is presently the Dell EMEA pre- and post-sales senior manager for the Dell Advanced and Big Data Analytics solution. So thanks for being with us today, John and Nuno. We're looking forward to your presentation. You know, there's no better source for tricks of the analytic trade than John Elder, an established industry leader renowned as an acclaimed training workshop instructor and author, and well known for his top 10 data mining mistakes and advanced methods like target shuffling. So in this webcast, Dr. Elder, who's the CEO and founder of Elder Research, North America's largest pure-play predictive analytics consultancy, will cover his top 5 methods for boosting your practice beyond barriers and gaining stronger results. So John, with that, I'm going to turn it over to you. You can begin just as soon as you're ready to go.
Thank you, Bill. It's an honor to be here. So today I want to talk about what I call the Fantastic Five. And you can see that in the background I have the images of some of my favorite characters, the Fantastic Four. And these are tricks that can help you get through a jam. And I'll spend not an equal amount of time on each one, but I want to fit them first into the cycle, the cross-industry standard process for data mining. So you've seen this before, but if you have a project, you need to understand the business, understand the data, model it, evaluate, and deploy it. Now I'm going to describe my things from the back forward. So from modeling, I'm going to go counterclockwise from around here, and I'm going to tell you what my 5 tricks are. Number 1 is an ensemble. Build multiple models to do the best job. Number 2, for data preparation, is to shape your distributions of your input variables to be well-behaved, specifically usually normal distribution. Everything does better when you have normally distributed inputs. And so if you can do a monotonic transformation like a log or something to make it more normal, good things happen. Going back to the data understanding, outliers can really be either mess up your entire project or be your entire result. Sometimes outliers are wonderful findings. Sometimes they reveal problems in the data, but they always will mess up your modeling. If there's an outlier in there and you can find out why it's an outlier, it's always valuable. 4th on the list, to iterate. Define your problem as you might want to change the goal of your problem by carving off easy parts of the problem or merging together some of the classes, and we'll look at some interesting examples there. And then the 5th one is to shuffle the target variable to get a baseline. Now, the hardest thing in modeling, and the most important, is to have a really good idea of how well your model is going to perform out of sample on new data, which is the only place that really matters. And a lot of times we use up all of our data. If it's not big data flowing at us, gushing river of data coming at you at all times, say it's a medical experiment where you've got a control group and very expensive, very precious data. If you look at it all and you use it all for training, you're going to easily overfit and have no idea how you're going new data. So this is a whole new, it's sort of a rediscovery of a way to get a much better feel for the evaluation. And I'm going to spend most of my time, more time on that one than any of the others because of its importance. But let me dive right in here. So, and we're using the Fantastic Four as our mnemonic to remember what these 4 characters are. So I'm going to relate each of the 5 things. The first is the whole team is the 5th thing, the ensemble. This came out in the fall of '61, about the time I came out, and was an interest. It revived the whole superhero genre. Prior to that, comics were westerns and romance and science fiction and monsters. And actually, Stan Lee had the great idea of making a monster on one of the good guys. So the scientists are always fighting the monsters. Anyway, they put the scientist, the monster, revived a Torch character, and have the fascinating Invisible Girl there. Okay, so the team just performs so much better than any individual one, and almost all the stories hinge around that, where together they can solve a problem. And this analogy works well for human teams, but it also works well for models. If you've got a model, and I'm showing here the lift chart for 5 separate tree models that are all trying to solve an insurance problem, which actually is more, the product is insurance. Here the problem was, is the person going to purchase the product or not? And so the data has been split into different subsets, and the out-of-sample results are shown as the outer gains charts, so lift charts there, where you would like it to lift up as high as possible over the 45-degree angle gray line, which represents mediocre random performance. And so each of the models does pretty well on the outside, but when you put them all together and average them, you get the one on the inside, which clearly has more lift, and it also has more decision cut points. These are decision trees that are being ensembled together, and the cut points are different if they're only the one problem with decision trees is everybody who falls into a certain leaf node all has the same value. But when you ensemble, a nice side benefit is when you're averaging 5 different trees together, you get ties much less often, so you have more decision points. And it's almost impossible to say this in statistics, but every single time I have ever seen an ensemble of decision trees, it has outperformed a single tree. So that is a remarkable result so far. If anybody has a counterexample of that, I'd like to see it. It certainly could exist. It's just particularly useful if you're using decision trees. It's also useful when you use other methods, and we've done a lot of problems over the years where we've combined multiple different types of models. Here's one for credit scoring, where it is better. And the graph there is showing a bar chart of what happens if you use one model. The distribution of errors has a median around 67 or so, and you can see the box and whiskers chart there. It ranges between, say, 64 and 74. But when you put two models together, the median goes down, and it goes down with every additional model. Now, it's not a panacea. You can see the outliers for the column 3. There's a particularly good model that combines neural networks, Mars, and polynomial networks that only had 55 customers that it got wrong that we gave credit to that shouldn't have. But there's also a combination of models that got 75 wrong. So there's no guarantee with the ensembles, but you can see with the trend line that it does very well. And these were simple ensembles, just averaging together the ranks of different customers according to those 5 different models. But there's a much fancier class of ensembles that's been developed mostly out of Stanford. And our book on ensembles talks about those and describes how to do those. But the good news is if you just build multiple competing models of different types or looking at different data, you can often get, and almost always get, a much better response. So it's sort of a secret weapon that isn't that hard to use. Once you've done all the hard work of data preparation, it's not that much more difficult to build separate models, which is kind of the fun part. Now, there is one major weakness of ensembles, and that is that they're very ugly. So there's a early Fantastic Four foe, the Super Skrull, and he had the powers of all 4 of them. So in a sense, he's a very nice example of ensembles, except he's a bad guy and he's quite ugly. So the ensembles are not interpretable, and this drives some people crazy. I find interpretability to be a benefit. I feel that too many people are led astray by believing in interpretation of their model instead of paying attention to the performance out of sample on new data, which is paramount. So, but that's you can get some arguments about that. In any case, that is potentially a downfall of the ensembles. But if you really want performance, it's the best way to do it that we know of. And moving on to the second one, we're going to use Mr. Fantastic to stretch distributions to normalize their shape. And this is really a simple idea. Statistics professor at the University of Virginia that I really admire mentioned this in passing once to me, and I didn't realize how valuable this is. But if you have something like distribution on the top where you have a lot of mass over on the left near 0, and then it dribbles out, it's often advised to take a log of it, and that improves things, the lower left distribution. But in this case, what is happening is you have a proportion that's being plotted, and the logit transformation is actually more appropriate, and that gives you the transformation on the lower right-hand side. Now, when you're working with the input data, if it's in raw form, is like the upper column, transforming it to be nearly normal with the logit transform retains the order of the things that were high on the top. It's monotonic. They're still the highest on the bottom. It's just they don't have the extreme influence that they might have by being outliers. They are more, and since all of squared error, which 99% of all tools are built around, works off of a normal distribution assumption, whenever you can transform your data to be normally shaped before you even hand it to the modeling algorithm, the better. Now, a decision tree wouldn't be so much upset by this, but pretty much any other method like and regression and so forth would be much helped by taming the input variables. So that's a simple and very valuable step. For our third one, we're going to use Mrs. Fantastic, the invisible girl. She used to be the weakest member, but a couple years after the Fantastic Four issue started, they gave her new powers where she could cast her invisibility and also make invisible shields. So she arguably became the most powerful member. But here we're going to use her power to make invisible outliers. Now, Anscombe put together a really neat quartet of data sets where you have distributions where there's a certain correlation between X and Y, and a certain least squared estimated line between X and Y, and that is identical for all 4 of these sets. There's about 85% correlated, and 3 plus 1/2 X is the least squared estimate for Y. Only the upper left really corresponds to the what we would think we had if we saw those summary statistics of R squared and correlation and so forth. The second, that one Y2 in the upper right, is a model misspecification. That would be exactly fit by a quadratic model. So the positive trend is turning over. And Y3 is kind of the one of interest to us. Well, Y3 and Y4 are the 2 of interest to us for this point. The outlier there is the only point that doesn't fit on a straight line, but it draws, because of squared error, any outlier has huge influence on where the line goes. So it draws it upward here. If the outlier had been sufficiently low, then the whole line and trend would have gone negative, even though 10 out of 11 points are going positive. And that can be found by looking for large errors in your model. If you fit a model, always look for the largest error and look at those points. Those are usually very interesting points. But there's a subtler problem on number 4. There's the influential point, the leverage point is called, has 0 error. The line goes right through it. You can see that it's an outlier in the X direction along the horizontal axis, and the entire slope of all the data is defined by that one point. And this has actually happened in practice. We've seen very often when you have a typo in the data or something. Again, the decision trees wouldn't be as affected by this because if something is greater than 10, it doesn't matter if it's 11 or 1100, it'll head one way. But any of the squared error, model fitting, trending kinds of models would have trouble with this. So it's an outlier in the X direction called a leverage point. So if you can identify those things and figure out what's going on, that value could be a legal and honest value. So could the one on Y3. In fact, that is reminiscent of a problem that I heard about with the hole in the ozone in the Antarctic. There was saturating the measurement device, and they went out in the Antarctic and replaced it a couple of times before they realized it was an actual radiation measurement, and it was a discovery. So in that case, the outlier was a discovery that there was a thinning, or colloquially known as a hole, in the ozone layer seasonally that was allowing excess radiation in, which could be very dangerous if it happened over inhabited areas. So naturally, a lot of outliers are some kind of data entry problem. We worked for the Social Security once, and there was a database of people having that needed help for disability. Some preborn infants or older people that had injuries and so forth. Anyway, there was one 800-pound baby in the data that made it positive correlation between birth weight and health outcome. Well, obviously it was either an 800-gram baby or something. There's an error of some kind. Then you took that one outlier out, and now there was a negative, as you would expect, correlation between birth weight and health. So one outlier can either be the answer or it can hide the answer, and it's extremely important to identify them, whether they have large residuals or errors or not. Done a lot of work in the stock area and just getting the split adjusting and the dividends right. Otherwise, the optimization will be dominated by what looks like a disaster day when really it just split 2 for 1 or 3 for 1. We have a good positive example in the direct mail world where we had some oddnesses we were noticing in the data. You really, if you're doing data science, you really need to be kind of like Monk. He's sort of like Sherlock Holmes with all sorts of disorders, but that ability to focus on details and figure it out, it can save the day sometime. And when we were able to hunt down why certain people weren't getting catalogs as often as they should, it revealed that the Merge-Purge house had been accidentally deleting all international customers from the sales catalog. So we were able, that was one of the contributors to doubling the sales per catalog by finding that inconsistency. So visualization can be extremely important, and then obviously figuring out what's going on with the outliers and doing something about it can make the model much more valuable. All right, going on to, well, I'm sorry, just one, I can't help but we love cutting edge research ideas. just want to mention briefly in passing, here are two really neat ideas. CADE, Classifier Assisted Density Estimation, the idea is basically label all your data as non-outliers, fill the space of your data with a bunch of fake data that you label as outliers, and then build a model to separate the two. Then any one of your own data points, actual data points that's really a 0 that is fit by the model closer to a 1 is a prime candidate for looking into as an outlier. And it's just a clever, simple idea, came out of UMass Amherst. Professor Jensen and his students, we recommend it. We've used it valuable. And then one that I had with Yi invented something called generalized degrees of freedom, which calculates the true complexity of a modeling algorithm, and I've written on that. And a byproduct of that is that complexity is assigned to individual data points. And so obviously ones with high complexity are definitely worth interviewing, let's say. All right, so love to talk endlessly about those. Let's go to the fourth one. The human torch is going to help us fuse together or burn away parts of the problem to redefine it to an easier one. So these are you mess with the problem definition and don't just take it as it has been to see if something shakes loose. And let me illustrate that with examples. For instance, we once had a problem working on at the University of Virginia Hospital some respirators. If you have this valuable, expensive piece of equipment that's in use for people in very poor health that need assistance breathing, how do you schedule these? How do you know if one's going to be available? If a patient is being sent to your hospital, or they need to be sent somewhere else? So just from a pure sort of cold-blooded business standpoint, you're looking at the use of the machine, and you can think of a health trajectory as sort of getting better or getting worse or staying the same. The interesting thing here is that the outcome of the respirator being available, you'd think there's two outcomes. It's either available or not, and trying to predicting the load on it a week from now or something like that. The respirator will become available if the patient has a positive health trajectory or a very negative health trajectory. Very different end state for the patient, same end state for the respirator. And when it won't be available is when they're in sort of a static position. So by breaking the problem instead of two problems, is this going to be available or not, break it into three state problem. Is this available for a positive or negative outcome, and is it unavailable because of sort of static problem, actually makes it much more possible to predict the availability. So it's kind of a simple, sort of obvious after the fact, but nothing's ever obvious before the fact. Another good thing to do is to not say my model has to give me E equals MC squared or force equals mass times acceleration. It doesn't have to give me an equation that's good for all time, like a physical discovery. It just needs to answer my question, and it can be a combination of models. You can break a problem and solve one with a simple model and another, and I'm going to give a couple of examples of that. And but before we go to those examples, just say a hint that will help with some of these things is build a one variable shallow tree to uncover either leaks from the future if something works too well, or to uncover some certain variables. And I can tell some horror stories around that. The top 10 data mining mistakes, which is chapter 20 of the first book, and also available from our website at Elder Research, tells you all sorts of stories around these things. But let me talk about this splitting off the problem. We worked on a problem once with identifying the species of different bats from their amazing echolocation signals. And here's a plot of about 100 or so signals from 6 different species of bats. And you can see a visualization, 3 of the features that have to do with the time and the frequency analysis of the chirp that the bat to navigate, and also they can even tell texture apparently from the echo of their signals, which is astonishing. So the classes are shown there in a 3-dimensional feature space, and 5 of the classes fit in a box, and you can see there's some overlap, but there's some clustering. It's a really interesting problem. There's enough information in those features to do a good job of classification, but it's not by any means trivial, like let's say the versicolor petals, the three-dimensional Fisher problem that's often used. It's got much more overlap than that. But there was one species of bat that was way off the chart, shown off there on the left as species F. That was a big-eared bat, and because they had physically big ears, they were able to use much lower frequencies for their signals than the smaller bats. And so just one feature, hey, what is the main frequency, carrier frequency that this bat is using? If it's over a certain threshold, it is the big-eared bat. That's all you need. So you've got a 6-class problem with a confusion matrix of 6 by 6, and by just one feature, you can snip off one class, get it accurately, and turn it into a 5 by 5 confusion matrix, which is a very simple, much simplifier more than you might think, going from 6 to 5. So the idea is, if there's an easy part of the problem, snip it off and have the computer work on the hard parts of the problem. And if you take this to its extreme, that's known as the gating method, where you identify something that sends you down, a gate that sends you down 2 different paths, and you can do that multiple times to decide how to break your problem up. So don't be trapped into thinking that your model has a one-size-fits-all, that your model has to solve the entire problem. You can break it into parts, and then at other times you want to fuse parts together. And an example of an iterative, sort of breaking it into parts iteratively, some work that we did years ago for Anheuser-Busch. They wanted to identify products on the store shelf from a picture. They have the computer automatically identify the exact stock keeping unit that was being involved. Bud Light 12-pack, 12-ounce, sideways, etc. And so we took a lot of data. We actually bought a lot of data and had a lot of beer in our office. But anyway, that was all for research purposes. And we also took pictures in the situations out in the grocery store. I remember a big burly guy. We were taking a picture in a 7-Eleven, and we're taking a picture as he's reaching for this massive beer. And we said, "We'll wait. We don't need to document this action of yours at noon." But anyway. He gave us a dirty look. But we got the data. We got the data of what it looks like to have beer on a shelf, and then train the computer how to identify the most common products to be able to automatically fill in with 90% of the what they call program, which relates how the placement of the products relates to sales and things like that. So technically, it was a big success. And one of the breakthroughs was to do it iteratively, to first get some of the junk out of the way by modeling and figuring out what the background was. So here we have a black and white version of that picture, and we've identified that the gray areas are the background. So that is masked out and replaced by noise. And then we go in and iteratively look for matchup templates to the ideal picture. And identify. Some of them are very easy to identify, as shown by the yellow circles here. And then when we take those out and replace them with noise, we have a simplified problem that a second pass can work with, and we can end up with very high accuracy. So that breaking a problem down into parts and solving those parts with different methods is a very powerful trick. Now I'm going to get to the very last and most important of them, represented by the thing. Using brute force, we're going to target shuffle to measure baseline performance. So target shuffling is the name that I give to the idea of figuring out what the ability of your powerful software is to torture the data until it confesses. Can it find something when something really isn't there? So what we do is we build a model as before, and we store its strength. And then we take the target variable, the output variable, disconnect it from the rest of the variable, shuffle it around, and reattach it. So now we know there is no relationship between the inputs and the outputs because we've given everybody somebody else's output. The histogram of the outputs are the same. They've just been assigned to different people. Now we use our powerful modeling technique to try to do the best and find something. And there is going to be something out there. There's going to be something correlated with the output, even though it's meaningless. And we store the strength of that result. We're not that interested in what the result is because we know that the cause and effect is completely random. But the more variables we have, the fewer cases we have, the easier it's going to be to find something that's positively correlated with the model. Now, what we do is we do this many, many times, maybe 1,000 times. We break apart the output variable, shuffle it around, and reattach it and refit a model. And we get a distribution of the results that we're going to have, telling us how to where those things are. Now, since we have a little time here, I am going to actually show this process in a little more detail for an example, and then jump back to the very end of the talk. I'm going to show an example. What on your screen is the strike zone for all the pitches, the strikes thrown on June 1st, 2013 in Major League Baseball. So the x-axis is the horizontal position, the y-axis is the vertical position, and the depth is the pitch velocity. So the deeper it is in the box there, the faster the pitch is thrown. We have all the strikes in the zone there are represented as dots. The red dots were the ones that were hit. So a hit is a pretty hard thing. You've got to connect with it. It's got to go fair. Nobody's got to catch it or tag somebody else out before you get to base. So only 9.4% of all those strikes thrown in the strike zone on that day were hits, and those are the red dots. Now our question is there a hot spot? Is there a particular subset of that strike zone where hits happen a lot? So we're going to go through, and we're showing position number 1 right now, and off on the right in kind of a small type, sorry about that, is that there were 2 hits and 11 strikes, and so 15% of the sample, and the p-value for that is 0.4. Now, p-value close to 0 or close to 1 would be really interesting. Anything close to 0.5 is exactly what we're expecting. So the p-value is very nice as a way of saying if I have one idea and I want to check it out, I have a 15% hit rate with 13 pitches. How does that compare to a 9% with hundreds of pitches in the overall population? And the p-value tells you what the likelihood it would be that if you drew random ones out of a set that large with that concentration, that you would get that finer concentration. So we're going to look at a few of the charts, and we see that other spots have different p-values. Here's one with only a p-value of 6 or a 6% chance that out of 5 pitches in that zone, 2 of them would be hits. Not higher because it's only a very small sample size. If we had a large sample size, the significance would be much greater. Then if we look at a couple of more examples, here there's 9 out of 37, so there's only a 1/3% chance that would happen. So we're going to remember that one because that's a really good one. If we go to a place where here there's only 1 hit out of 28, so it's a particularly hard place to get hits, that's significant in the other direction. You see the p-value is closer to 1. It's 0.76. So we explore the entire space. We look at, there's about 40 different chunks that have samples in them, and we're going to look at them all, and we're going to remember the very best one. So the very best one was that 11th one that had the lowest p-value of 0.35%, or 1/3% chance that you could get that many hits. 24% of them are hits when there are 37 pitches. That's pretty significant. And if we had just tried that idea out from the very beginning, there would only be a 1 in 300 chance that we could have gotten something that interesting if it truly was no relationship. So under the null hypothesis that there's no relationship, what is the chance that we would actually find the relationship this strong? And it says 1/3%. So why can't we use this significance as the significance of our model? Our model was to find the subset that works best. And the problem is we've cherry-picked. We've done multiple comparisons, and we've taken the very best one out. To truly test how well how truly significant this is, what we have to do is target shuffling, which will tell us how likely we could have found a really cool spot this interesting if there was no relationship between hits and pitches. So let's set up that experiment. We're going to take the original data, and we're going to change which ones are red, and then that's what I've done here with this one. And then we're going to do a search. Well, just for good purpose, we're going to change it again. Then we're going to do a search over that. And in this new definition of which ones are red, we've shuffled all the pitches, or the points in three-dimensional space are exactly where they are. We've just shuffled the colors around, which represent the hits. And now we've looked for the highest, most significant concentration of reds versus blues. And in this reality, alternate reality, it's in a different location and has a 1.7% chance of happening. We shuffle it again and search again, and we find another location that is now an alternate reality that didn't happen, where there's a 2.8% chance that something this interesting could have happened. And we do that several times and build up a histogram. You can see on the left is a search. We're finding a location, and that one is a fraction of a percent chance of happening to be 33% hits in a sample of about 20 hits. And so we're tracking our results on the right-hand side with a histogram. Our true result is the red line, and each of these blue things in the histogram is a count of how many results were worse, which would be off to the right-hand side, or were better, which would be close to 0. We're plotting the log of the p-value, so lower values are more interesting. Now, we're going to run this several times, and we have 40 trials there, and we'll run that. And after 100 trials, it turns out that 15% of the random trials are better. 15% of the mass of that histogram is on the left-hand side of that red line, meaning that when there was absolutely no relation between defined as a hit and what was actually a hit, we still found much more concentrated areas 15% of the time. Now, maybe 100 trials isn't enough, so we run it 350. The number changes to 17%. We decide to stop at 1,000, and it's about 18.4%. So after the 1,000th trial, 18% of the time, our randomized shuffled data was able to find a more interesting result, better p-value, than our real result. So what we have here is a much better measure. We now know that our original result wasn't 1/3% chance of chance, it was 18% chance of chance. So there's an 18% chance that it's just an arbitrary finding and not real. But 4 out of 5 times it held up. So I would find this it wouldn't make any publications because of the artificially low against values that they use, but that's a story for another day, how very many published results, the vast majority of published results in discovered medicine, for instance, are false because of this multiple comparison issue. So that needs to be fixed. So maybe we wouldn't be able to publish it in a journal under its current setup, but a business owner, a owner of a baseball team or something, would be very interested in this result, either for offense or defense, that there's a 4 out of 5 chance that it's real and not chance. And so target shuffling, a very simple method to program, is extremely valuable for the most important thing, which is how likely is my result to hold up in the real world. So my final slide before I turn it over to Nuno is summarizes these points. Going backwards, we used the brute force of target shuffling to evaluate our model, to figure out a baseline in the very beginning. In the first place, with the Human Torch, we either fused together or burned apart different parts of the problem. We redefined the problem to make it work well with modeling, and then put it back together better than before. The third idea was to detect and eliminate outliers. Don't just click on inconvenient points and get them out of the way. Find out why they're outliers, what the underlying reason is, and in some cases, that's more important than the whole model. Just one example, we worked on some software usage trajectories that different people had, and discovered that the inconsistency in the data led to the discovery that there were a lot of unauthorized users of the software. And so that was not suspected by the client, put a halt to the whole project till that problem was figured out, but it was of more value to them than the entire original project. So sometimes the data artifacts of the outliers are more valuable than the model. Back at number 2, we shape distributions to be well behaved in ways that retain the information, don't change the order, don't rank transform the data, for instance, because how will you know what to do with a new data point. You need to have a formula that's monotonic, that maintains the order, but reduces, again, it's a form of reducing outliers because outliers have far too much influence and leverage. And then suggestion number 1, don't just build a single model, build an ensemble. And so we're going to have questions at the last 10 minutes or so, so I'll hold off for that. But I would like to turn you over to Nuno, who will tell about the implementation of some of these ideas and also some new developments.
Well, thank you very much, John. I really appreciate your presentations. They are really interesting. I would like just to point out that you always share sound knowledge, not only scientific, but also empirical. And I think this is fair to be pointed out. You don't just talk very generically. You really bring effective knowledge to your presentation. So I'm really glad, and it's an honor for me to be sharing this small space with you. Thanks, everyone, for this opportunity. So I'm just going to talk a little bit about Dell Statistica, what is Dell offering in this space, and how can it help you regardless of your being a data scientist or a business user who wants to bring and extract knowledge from your data. In order to create a coherent transition from John's presentation, I'm going to start by just mentioning very rapidly some of the features that can be useful in order for you to use the tips that John has provided us. So if, Bill, if you can move to the Statistical Analytics Improves Insight slide, I'll be thankful. Please. In the ensembles, you can open Statistica and you can really create a workspace where your model ensembles can be created, but not only created, you can be offered with tools that allow you to evaluate their quality and performance, or also to combine the responses, the predicted responses for your response variables. Not only you can have your workspace defined for this purpose, but you will also be provided with a response optimization tool in case you would be interested in doing some reverse engineering. For example, I want to know the best combination of my explanatory variables in order to achieve a certain value of my response variable. On the distribution side, you're going to have available for you a wide number of tools to test for the fit of your data to a certain number of theoretical or empirical distributions. Not only you can do this through statistical tests, but also graphically, where you'll have graphs that are objects you can edit, and in a very visually compelling way, decide visually also or show, give proof, visual proof of how good or not your data is fitting to a certain distribution or family of distributions. The outliers is another area that John has mentioned. Outliers, it's probably one of the richest offers within Statistica, either parametric or non-parametric. But most of all, I'd like to just point out the data health check notes that you can embed into your workspace, and it's going to not only detect and clean outliers for you, it can also perform a number of other tasks that are involved on data preparation and transformation, and those would include tasks such as handling missing data, accounting for collinearity, etc., etc. So invariant variables, etc. So you can really streamline all of these, having the data being run through this node, and have the data ready for downstream without the need to be performing repetitive tasks. The shuffle and iterate, I'm going to point out also rapidly that it's going to be very easy for you to manage your variables, to create subsets and to work with them. You can mark them on the data directly or graphically. You can select them graphically. You can also create new categories, categorize variables, work with subgroups. But most of all, you can, if this is published in R, you can use R scripts and open them and have them embedded into your workspace. And you're going to have all the advantages that this workspace offers in terms of security, streamlining automated actions, etc., rules building. You can have your algorithms very empowered in this scenario. Just to finish, that if you can also develop your own customized application. So Statistica offers you standard language in the market for scripting, preventing you from being dependent from the provider. So you can use Python or Visual Basic as scripting language to develop your own customized applications within Statistica. So focusing on John, this is a very brief presentation necessarily, but now let me be more generic. And as a data scientist, as a manager, as a business user, what do I want on my perspective that can be offered by a platform, by an analytical platform? And I believe Statistica can offer you, and you can seriously consider it as a viable alternative among the ones you can be testing or evaluating for your projects, for your company, for your organization. You'll have a tool where you can use novel algorithms, not just the ones that Dell develops, but also the capacity to bring algorithms either from the R library or from external models using what Dell calls collective intelligence. So you can bring external models. A model that has been developed by John could be inserted into your workspace, could give you the predictions, or you could use as a reference to test if the performance of your own model built over your own data. You're going to need a menu-driven application that allows you to save time on repetitive tasks that you have to do very frequently, but they consume a lot of your time. So this is very important in terms of the performance and the effectiveness of your projects. You can also, you will have also a platform where your work can be deployed very rapidly and made available and visible to the whole company, to your colleagues, as long as you allow them enough level of permission. And finally, you want that when you create models, when you create access to data, when you create reports or business rules, you'd like them to be automated so that anyone, even a non-expert user, can use and can run them. They can be reached by the click of a mouse. So let me just share with you 3 key takeaways on what Dell thinks that it's going to be the future of analytics and how we are contributing to in shaping that future too. So Bill, can you please move to the slide, the next slide, please? So one of the points is Dell is investing resources in order to empower more people. So we are making our analytical tools easier and easier to use. You still can access all the needed complexity if you are a data scientist, an experienced user, to develop your models, but we are making possible to democratize the usage of your work and make it available to a much wider audience. Bill, if you can go to the next slide, please. We are investing on reducing time to intelligence. So we are creating ways of having the results closer to the sources, closer to you, and easier to see and interpret from a visual standpoint, and in a way that you can interactively play, let's say, in commas with the results and check how the model can impact in, for example, subgroups of your population. And next slide, please, Bill. And finally, and perhaps the most important, Dell is allowing you to embed analytics everywhere, meaning that now with Dell Statistica, and this is a breakthrough and a novel in the market, I believe makes us different, you can not only deploy the models on the data sources or on the gateway that's collecting data, you can also have all the modeling process being run natively on the data source. So in order to flag, Dell's motto is now empowering more people, reducing time to intelligence, and embedding analytics everywhere. Thank you very much for this opportunity. I'm going to pass to Bill now for the Q&A session.
Well, John, Nuno, thanks for that excellent presentation. And we'll get started with today's Q&A session. And I want to thank the audience for their participation. We've had a great many questions that have come in, and we'll do our best to get through them all in the time remaining. So during this Q&A session, I'll leave up this screen with contact information for Dr. Elder and Nuno if you'd like to contact them following today's webinar. So let's get started. John, I'm going to try and organize these into the same 5 steps that you talked about. Let's talk briefly about shaping distributions. There was a question about whether or not shaping the distribution of the data would help the non-regression methods, such as support vector machines or neural nets.
Yes, definitely with neural nets. One of the things about neural networks is they have to use all the variables that are handed to them. They don't do variable selection, the normal neural nets. And they have to use up a lot of their power to learn that a variable is trouble and to give it low weight and so forth. So anytime you can do good variable selection or feature engineering, it dramatically helps the neural net's performance. And so the neural net is at its heart working with squared error. And so if you have a skewed distribution with very big outliers, they'll have far too much influence. So yes, it desperately helps with that. I have less experience with the technique with support vector machines. I suspect it would, because they're also looking at separating the space, and that the space is defined by input variables. So any kind of taming of the space tends to help a lot.
Oh, thank you. Now, there were a number of questions that came in on ensembles, and I know that's really a very broad category. So let me try and break this down into just a couple of subsets. There is a broad question about how these teams of models vote together. Do you simply average them? Do you add them? Do you use other methods? What is the voting method that allows the group to be stronger than a single model?
Yes, good question. So the two most popular methods are of combining are averaging and voting. So you run the models are separate. They can be separate columns, and then they either make let's say they vote, they make a decision, accept for credit or don't. And they don't give a strength for that. They just give their final decision, and then you need a majority vote for that amongst the models as your ensemble decision. That has certain advantages. Another method would average the decisions, say it's between 0 and 1. They would average them together. That way a few very confident votes or predictions would outweigh several wishy-washy predictions. And so you have to look at your application and see whether it's subject to outliers or not. If they're bounded between 0 and 1, averaging is not a problem. If you have estimates that are unbounded, then one single bad estimate can mess with the average. That doesn't happen with voting. It's more robust. Bagging and boosting are the two most popular ensemble methods, and boosting is iterative. Bagging just combines them, as I've described. I think a lot of different ensemble methods, even the simple ones, tend to add value, and there are some very sophisticated ones, and I'd refer you to my book on ensembles for that. And I'm mostly in that book, mostly describing the work of other people, because it's really been picked up in a lot of areas.
Right. I know I've been working in that area myself lately, and so, most of us reach for random forest for bagging or GBM for boosting, and I'm still trying to figure out about super learners in stacking, which is much more complex. Yeah. Now, one of the interesting contradictions almost of ensembles is that if you had 10 models that you were combining together in a group, it's likely that one of those models is actually stronger than the average, although your experience and my experience are the same, and that is that ensembles are universally more accurate. So the question comes, is there some way then to look at the individual models in a voting group and to pick out the ones that are stronger and discard the ones that are not stronger?
That is a fascinating topic, and the full range of experience is possible where your ensemble could be better than any of your existing models, and that is more likely to happen than the opposite, where it's worse than any of your existing models. But I've seen both. Typically, it's in the distribution. One of the beautiful things about ensembles is it lowers the variability, so your result may not be the very best result if you happen to know ahead of time which was the very best model, which that's the fatal flaw, is you never know which one's the best ahead of time, but it reduces the variance in the results. When you have think of it as a board of directors, you have different people with different expertise on the board, but they have to compromise to make a decision in some way. The decision is going to be less risky than if any one of them was emperor. So, and that just, that holds up kind of universally. So ensembles reduce the of your result, and they happen to also have the magic of reducing the bias of your results.
Right.
It's an interesting open question to look at a bunch of models and be able to figure out which one is going to perform best on new data that you haven't seen before. And I'm interested to hear if others have learned more about that area. But in the meantime, I use ensembles.
Right. Yes. Okay. So I believe this falls in the category of your iteration comments. When you talk about carving up the problem into its parts, is that different than simply saying let's make sure the data is homogeneous and starting with segmentation, or is there something more fundamental about carving this up that you're heading toward?
I don't know if it's more fundamental. I think the important attitude to have is, instead of taking a problem and saying, I've got to solve the problem with one model, is look at your data, see if you've got a mix of different parts. Maybe you've got students at a university and some are day students and some are night students and some, it might be better to build separate models for them, and it might not. And you might try to combine things or to separate them and see where the best gain comes from. So, you have to be pretty nimble and try different things. And I find that stories really help there, telling, stories of what happened on past projects, even when they're completely unrelated, tend to, I guess people, nod and smile, just wait for me to be done with the story. But anyway, it does sometimes spark an idea about the particular problem. And so there have been a lot of cases where kind of messed with the problem definition and interactively with the data to find where the best match of problem that we can solve related to the problem that the client really wants to see solved. And partly defining the error metric correctly, defining whether you've got subsets that are homogeneous enough to be dealt with separately, or whether the model be richer by handling all the data at once. It takes some experimentation.
Right. Okay. And I think we have time for one last question. Would you explain a little bit more in detail about what you mean about information leaks from the future?
Okay, so that's one of the top 10 data mining mistakes, and probably the most common is when you have data that you're supposed to know. Let's say when the person is first a customer of your company, who's going to be a really great customer, but you've updated your records and now you know they're married, they've moved, you've got all this information that you didn't know when they first joined you, and you allow that information accidentally to be available to your model. Kind of a sad and funny example was on the insurance problem. We had a variable that was 100% accurate. It was present for a quarter of the data, and every time it had a non-zero value, it was 100% accurate of predicting who would buy insurance. And people were very excited, and okay, the carving off problem, we've got a quarter of the problem solved, now let's move on. Well, anytime you have a variable that's 100% accurate, you know you've done something wrong. It's too good to be true. Long story short, it turned out to be the cancellation code for the insurance. So it was either fax or email or phone call or whatever code they had. That's how they canceled their insurance. So naturally, anybody who could cancel insurance was a purchaser of insurance. It just, the order of time was wrong. So because your data is not usually kept for the purpose of modeling and kept pure and, here's what we knew at this time, you have to work hard to kill the leaks from the future, the anachronistic variables that have slipped in that give you this feeling of awesomeness. And your model will always be worse when you do that, when you get rid of it, but it will actually be useful. Oops, I lost y'all.
John, I think we can still hear you.
I can hear you now.
Okay.
I'm done with my point.
Okay, so it looks like we lost Bill. I think we're almost done.
Yeah, John here. I got audio back. I think we are done. And
John, thank you. I'm back.
Yep.
My audio dropped momentarily, so thanks for everybody for covering for me there momentarily. But John, Nuno, thanks very much for some great answers to some very good questions. For those of you that asked questions that weren't answered today, we'll be sending all the unanswered questions to Dr. Eldo and Nuno and the Dell Statistica team so they can follow up with you after today's webinar. I have just a few quick announcements. So if you'd please mark your calendar for June 14th and our next DCS webinar, which is the Internet of Things case study using big data to create operational efficiencies. And that's going to be sponsored by Qubel and the Google Cloud Platform. Also, today's taping will be available for on-demand viewing later today and can be found on the home page of Data Science Central in the Webinar tab, located at the top of the page. Well, that concludes today's webinar, and I'd like to thank our audience for their attendance and thoughtful questions, and a special thanks again to Dell Statistica for their sponsorship, and our speakers today, John Elder of Elder Research and Nuno Antonio of Dell Statistica, for their insights into today's topic. My name is Bill Vorhies. I'm very pleased to have been your host for today's event, and I look forward to seeing you all again on June 14th. Have a great day.